Well, it's a true honor to be able to begin this talk about exploring distant worlds with the James Webb Space Telescope. I'm Dr. Nestor Espinosa, and I'm an astronomer here at the Space Telescope Science Institute. I think there's no better way to introduce and explore the idea of exploring distant worlds that the concept of our own Earth, this big planet that looks, for us humans, very, very big. That's exactly what we are located right now. This is our current location. Our current location is actually one of the planets out of the 8 or 9 for those of you Plutonian fans out there. So this picture is a different perspective of what our Earth looks like. This is a selfie that was taken by the Cassini spacecraft that was going around close to Saturn. And this little dot that you see with an arrow, that is our Earth. That's exactly where we are too. This is an image that should make you feel a bit small, but if this is not doing the trick for you, consider the following image, which is a picture of our galaxy. This is not a selfie anymore. We cannot go outside our galaxy yet to take selfies. But this is a very good model of how our galaxy looks like. And our sun, the star that we orbit around, that is only one star out of the 100 billion stars in this galaxy. If this still doesn't do the trick to see how small we are, consider the fact that our galaxy, this galaxy, the Milky Way, that holds its 100 billion stars, is just one of the hundreds of billions of galaxies out there that are going around in the universe. So this is an actual image. Again, it's not a selfie, but it's an actual image of galaxies out there. Almost every point in this image is a galaxy. And our galaxy, is just one of those galaxies out there. So that's where we are. So this makes you think, right? This is a big universe. There's a lot of stars. Again, 100 billion stars per galaxy and 100 billion galaxies in the universe. That's a huge, huge number. So imagine the possibilities out there. Imagine the possibility of having planets orbiting those other stars out there. Here's a very interesting statistic for you. On average, we know that there's out there in our galaxy at least one planet per star. Think about that the next time that you go outside and look at the night sky. Just pick a random star, and on average, you should be pointing not only to a star, but at least to one planet. Now, we know of the existence as of today of in the order of like 5,000 known worlds orbiting other stars. We call these objects exoplanets. This is short for extrasolar planets, planets that are orbiting stars other than our sun. And the whole concept of this talk is not only tell you about these objects, but also tell you how Webb is exploring these exoplanets out there. Now, Webb is revolutionary in terms of the technology that it has. And to understand how revolutionary it is, I think it's important to understand the concept of our reality out there. So the colors of light that you're observing right now, if you look around you, all the colors that you've experienced in your life, those are just a tiny bit of reality. What I'm showing here is a spectrum of the colors in the universe, and the visible colors, the colors that you see, are only a small fraction of that reality. In reality, there's many other colors out there. Here are some colors that you already know. The radio wavelengths, you probably heard of them. Those are radio waves that are going around that we interact with all day through our cell phones, through communication systems, and so on. And there's microwaves too, which we use to heat up our food. So these actually are colors of light that we have that although our brains cannot capture them, our eyes cannot see them because our eyes are trained to only see visible light. We do interact with these other colors of light, and we do know how to measure them. Well, telescopes like, for example, the Hubble Space Telescope that has been in space for a while now, they are able to see mainly visible colors of light and a little bit of ultraviolet and a little bit of infrared light too. But the James Webb Space Telescope actually enabled us to see a big chunk of this infrared light that is out there. So JWST, this Webb telescope, it's an infrared telescope that can see where our eyes can't. Now, you might be wondering why it is so interesting to see in the infrared, and why did you build a space telescope to look in the infrared? Well, first of all, These wavelengths of light in the infrared are extremely interesting because they are the wavelengths of light in which molecules like carbon dioxide and water out there, which are important molecules in our solar system planets, and in particular for life on Earth, that's exactly where they emit and absorb. So we want to understand those colors of light. But also interestingly, everything that you have around, everything is emitting in infrared. If you look at buildings, for instance, if you look at the floor, and if you look at your favorite pet, everything emits an infrared light. And this is exactly the reason why we needed to send Webb to space. We send Webb to space so it can be far away from the Earth and the Moon, so they wouldn't interrupt the light that we're trying to gather from objects in the universe. Webb is in this 1.5 million kilometers orbit from Earth, this L2 point, and it's kind of co-orbiting with the Earth in its movement around the sun. Now let's jump to exoplanets. So what I want to introduce to you today are what I like to call the JWST greatest hits ever. Of course, cannot do ever because Webb it's been only 2 years since it was launched. So we're gonna give you the greatest hits so far. And of course, I don't have the time to get you through all the amazing discoveries that Webb has done. So I'm gonna give you a little taste of what are one of the greatest hits, according to me, of what Webb has done for exoplanet science. Because the greatest hits concept is embedded into the music industry, I decided to bring titles to this thing embedded in music. And the first science hit that I'm going to show you is I entitled it Survivor, which has to do, of course, credits to Destiny's Child. And it has to do with planets that have survived their environment on their crazy stars. To this, I think it's really interesting to introduce our own Earth into this concept. So we see the sun every day, and it looks like a very quiet star, more or less. But this is out to change in around 5 billion years from now in the future. So in 5 billion years from now, what's going to happen is that the field at the center of our sun is going to change. That's going to make the sun to expand, and it's going to convert in what we know of as a red giant star. What this will mean is that it will expand so much that you will, if you survive 5 billion from now, you will see it very, very large on the sky. And actually, as you see in this video, you see the Earth here surviving. Well, there's some models that show that the Earth might not survive this expansion of the sun. It might be that the Earth gets engulfed, and then bye-bye Earth. Now, don't despair. I know this might be a bit disturbing to see, but this is happening in the very, very far future. We're talking about 5 billion years from here. It's beyond our comprehension time-wise. We've only been around for a few thousand years, so we're fine. Humans, I mean. But let me show you to scale more or less what this means. So the sun is something like this. So I'm going to put this to scale. And the Earth, it's over here, and it looks very small. These sizes are to scale because it's hard to see the Earth. I'm going to do like a close-up. So this is the Earth. Now, when the sun starts expanding, it's going to leave behind the core, basically, of the sun. There's going to be a big chunk of the mass of the sun embedded into a very, very small ball. Now, how small? Here I'm plotting, again, at the center of the sun. You can see it, this little white dot. That is going to be the core that's going to be left over from this expansion. We call this a white dwarf. It's going to be more or less the size of the Earth. Now, the interesting bit is that we don't know, again, if planets like the Earth will survive. And we don't know if what's going to happen to planets like Jupiter or Saturn or Uranus and Neptune and all the objects out there in our solar system. We didn't have data on this until now. So what I'm going to show you next, it's a very, very exciting result from JWST, in which you can actually take pictures of these white dwarfs to try to see if they have planets going around them, which is very, very, very exciting. So I've entitled this potential pictures of planets around these white dwarfs. Excitingly enough, this is work, there's some teams working on this around the world. And one of these teams is led by Susan Maloney, which is actually my office neighbor. And she has a team that has led some imaging of these white dwarfs out there in other white dwarfs that are going around in our galaxy. And here are two pictures of these white dwarfs. So these dots that you see in the center, those are actually these white dwarfs. So these are these future sun. I know they don't look like beautiful pictures of the photos that I just, or the video that I just showed you. But this is actual flux coming from these white dwarfs. And what Susan and her team have done is to remove the image of this sun, of these stars, in order to see if there's a planet orbiting around them. And she actually has detected what seem to be like planet candidates that they are uncovering with this. Now, these are planets that are very big. We're talking about planets that are like more massive than Jupiter. But still, these are the kind of planets that you're looking for. You're looking for these survivor planets to see what the future might hold to like our own Earth, our own solar system planets in the future. I think this highlights a lot of what Webb can do. First of all, because as I told you before, you need Webb to detect these planets because they're emitting in the infrared. So there's no other way actually to detect these objects. So Webb is very unique in that it can go to these infrared wavelengths where planets like our own are emitting a lot of light, so you can actually detect them. And also, this is the first time that we're doing this kind of science. So seeing planets that have survived this red giant phase of objects out there, it's unheard of. And this is the first time we're gathering like strong evidence about them and learning about what the future might hold for solar like systems like our own in the future, which is pretty exciting. The second science hit that I brought you has to do with atmospheres, and that's why I'm entitled this Tell Me How I'm Supposed to Breathe with No Air, which is a song by Jordan Sparks and Chris Brown. There's another reason why I put this name to it, and that this is actually the name of a proposal that was written to JWST to characterize atmospheres of planets out there, which is pretty neat on its own. I don't think there's a better way of introducing the concept of exoplanet atmospheres than our own solar system. And in particular, I think a very big chunk of this is studying understanding our own solar system rocky planets. And to do that, I brought this ranking of terrestrial planets as vacation destinations. Like, yes, I ranked the planets as your better vacation destinations, and I'm gonna get started with that with Mercury and Venus, which are actually the worst planets to go in vacation. So Mercury basically has no atmosphere, it's too hot or too cold, depending if it's night or day. And Venus, on the other hand, is too much atmosphere. It's like too dense and it's too hot and cloudy. So hot and so cloudy and so much atmosphere that if you brought your car to the surface of Venus, it will be crashed off because of the atmospheric pressure. So really, you don't want to go on vacation to these objects. Mars is a little bit better. There's little atmosphere, but it has robots, which seem like a nice entertaining. And actually, they overcome the population right now in Mars. Is basically robots. And Earth, of course, is the best planet to spend your next vacation. It has a nice atmosphere, has Wi-Fi, and it's the atmosphere that is producing the air that you're breathing right now. I think introducing these planets in this way is very important because it lets you pass the message that the atmosphere that these planets have are very, very, very important. All these planets have order of magnitude similar radius and masses, but they have vastly different atmospheres. The beauty is that now we have the technology to actually make this remote detection of atmospheric constituents out there. So we can detect atmospheres of exoplanets orbiting out there. Now, this is really exciting stuff. It has one problem though. Small planets like these ones, like the rocky planets in our solar system, we wanted to see rocky planets out there and detect their atmospheres. They're too small, too faint, and too far away to be directly detected. So we cannot take photos of them. But we can detect their atmosphere through some techniques, very clever techniques that we figured out. The first technique that I'm going to introduce, it's called transmission spectroscopy. It's a very simple concept. It has to do with the fact that molecules have very, very detailed diets. So different molecules like to eat different colors of light. If you are lucky enough to see a planet passing in front of the star, which we know of many of them, when they pass in front of the star, part of the atmosphere will block light from the star as well. Not only the core of the planet will block starlight, but also the atmosphere. When this happens, different colors of light will block different amounts of light. Your planet might look bigger or smaller depending on which colors are being absorbed, of light are being absorbed in the atmosphere. This is the concept of wavelength here, of colors of light. And the concept again is that, for example, water likes to eat light in the infrared, these 2 micron wavelengths. So if you see that your planet is bigger in those wavelengths, then it might be that it has water, because it might look bigger because of the water might be absorbing part of the starlight. So the transit event that you're seeing here, this starlight as a function of, so you measure the brightness of the planet transit as a function of time, you can actually see that you have a deeper transit here at 2.3 microns. So you look for the molecule that absorbs a lot at 2.3 microns, and you might claim, the detection of an atmospheric constituent in here. You also can do the opposite. So when the planets go behind the stars, just before they go behind, you measure the flux from the starlight and the planet stays side. But when the planet hides behind, like plays hide and seek, you only measure the starlight. So you can remove the before and after to get the flux of the planet directly. You can actually measure the flux of the planets. Now, these two techniques have actually been exquisite in getting us compositions of planets in very much detail. So in these plots that I'm showing here, x-axis is wavelength, and the y-axis is this transit depth. And you can see these wiggles indicating the presence of methane, the presence of carbon dioxide, the presence of like a whole rich molecular inventory that we've detected thanks to these techniques. So we're using these same techniques to try to explore small planets too. And by the way, these wide colors of light getting all these molecules, it's a very, very first to us in the exoplanet science. And it's all thanks to the James Webb Space Telescope. So James Webb Space Telescope allows us to get this very, very wide range of wavelengths where many molecules emit and absorb, so that we can detect them with our models here on Earth and with these beautiful observations that Webb is getting for us. And typically asked, well, what is the most exciting planetary system out there for you? And my personal favorite is a system that is called the TRAPPIST-1 system. This is a system that it's only 40 light years away. That means that if you throw a ray of light to this star, it takes 40 years to get there. It's pretty near for astronomical terms. And it has 7 Earth-sized exoplanets, TRAPPIST-1b, C, D, E, F, G, and H. This image in particular is fantastic because it showcases the mixture of art with science. You see that planets that are too close, if they had atmospheres like the Earth and had water, the water will be in vapor form. So that's why you see vapor. The ones that are farther away, like TRAPPIST-1G and H, there's ice in the table. But the ones in the center, they might have water. They might have liquid water. We call that zone the habitable zone. It's like the right distance to be from your star, because you might have liquid water if you had atmospheres like the Earth. But that's a big if. We don't know if these planets have atmospheres or not. This is a very important system, and it's very exciting because it showcases the possibilities of having or no atmospheres in just one system. And this is not only an exciting system for the public, this is actually a very exciting system for the scientific community. So exciting that in total, the entire scientific community has devoted in the order of more than 400 hours of JWST time. That is a lot of JWST time to try to detect atmospheres on these planets. So far, through the techniques that I mentioned before, we know that TRAPPIST-1b likely doesn't have an atmosphere, so it's too close. It's so close that they start bombarding. It's just probably stripped the planet from its atmosphere. TRAPPIST-1c, which is the second closest, is still, the jury's still out on that one. But we're continuing to explore this planetary system. And we have actually, I'm working with some teams on some of these atmospheres and the other systems. So stay tuned for the near future. Now, this is not the only exoplanet system out there. There's many others out there that are worth analyzing and studying. And in fact, here at Space Telescope, we're starting a concerted effort together with the exoplanet community to try to figure out if other planets out there also have atmospheres or not, and why they might have them, why they might not, and so on. So this is a very, very exciting time to be doing exoplanet science. This is going to be done with both Webb and the Hubble Space Telescope. So it's very, very exciting because it's just the beginning, right? So stay tuned for the next few years on what might come up with rocky exoplanet science for small planet exoplanet science out of these Webb discoveries. So I hope that in this 20 minutes, I managed to shine a little bit of light on what Webb is doing, why it's so exciting, And I think we are in a very, very, very interesting time to be alive. It's a very exciting time to be doing exoplanet science, because we finally have the technology to make these detections, to make the detections of molecules on atmospheres of planets out there, of making these survival detections and so on, of atmospheres, in order to answer the big old question of, are we alone or not? So for any further questions, please feel to reach out, and I hope you've enjoyed this talk.
Hello, everyone. We would like to tell you a bit about the JWST universe experience that we both worked on. Let me introduce myself. My name is Milena Ratajczak. I'm an astronomer working at the Astronomical Observatory of the University of Warsaw. And I'm also part of the Science Now Creative Studio. That was one of the partners developing this experience. And I was responsible for part of the content creation of this experience. And together with me, there is Ola Birke. Ola is a designer. Ola is from Science Now Studio as well. And she was the creative producer of the exhibition and all JWST experience. This experience that I'm saying has been developed by the Science Now Studio in a partnership with the Leiden University in the Netherlands, and also NOVA and ESRON institutions. And as you may know, three of those partners are actually research institutions, and Science Now is a creative studio. So we thought together to create a bridge in between a researcher and general audience by using some engaging options for talking about JWST research, and not only images, but also to make it more immersive for the general public. So let me think about what was actually JWST universe. So in the moment when the telescope gave us the first images, people were actually stunned by its beauty, and researchers were stunned by its value, scientific value. And also those people who were working on technology or who were interested in technology, they were actually very excited about how technological marvel it is. So we decided to work on the ecosystem of formats that all created this experience that we call JWST Universe Experience. And namely, that was a photographic exhibition that used some images, beautiful images of cosmos that we have from JWST. Some immersive experience that gave us a dive into the beauty of science that it gives. But last but not least, the educational program that I guess many of us during this workshop are interested in.
So we started by asking ourselves, what if we treated those beautiful JWST telescope images as work of art? And that's what we did. That's how we came up with the exhibition format. So we designed the exhibition to take the visitors on a breathtaking visual journey, as similar you would experience it in an art gallery, and give them a little bit glimpse into the wonders of the universe. So the focus of the exhibition lies in a series of high resolution photographs that present the images that are presented then in a very big scale on light boxes. So the intricacy of it is even more highlighted, so to say. To build the narrative for visitors to the exhibition, we divided the whole story into 5 thematic chapters, assigning a series of photographs to each of the chapters. And then it was made for the visitors so that they could go through the experience chapter by chapter and learn more about the JWST telescope and its achievements that you can later see in the forms of pictures.
So, as it was mentioned earlier, we wanted to stress this special technological marvel that the telescope is. So, one of the chapters of the exhibition was about technology itself, and it shows one of the first pictures that JWST gave us, showing this super sharp star observed in an infrared. That's how JWST looks through the space. And it was one of the first calibrations photos when actually researchers working on it were amazed by the performance that this technological marvel is giving to us. This chapter of the exhibition was also additionally, we also had like a real model of the telescope, of JWST telescope, to show that we want to go beyond photographs, beyond those light boxes with beautiful photographs, but also have some 3D model that shows us all the important part of the technology that stands behind this images, and that gave us opportunity to show new ways of engage with the public, that it's not only looking at, but it could be also touching and looking more into three-dimensional things and technology. So the second chapter we named Other Worlds, and it was about photographs of planets, both in our solar system and also the one that are beyond solar system, so exoplanets. Here we can see the beautiful photograph of Jupiter, but we also can remember that one of the first photographs that we see, what we've seen from JWST, was actually the analysis of spectra of an exoplanet atmosphere. So that was also one of the part of this Other World chapter. And the third chapter was more, let's call it cosmological. So there are a lot of photos showing a lensing phenomena, gravitational lensing phenomena, and also some very, very distant galaxies. So the ones that were created almost just after the Big Bang. So it's from the very early universe. And the fourth chapter was about all of the life cycles of stars. So from its birth to its death, through many, many other evolutionary phases, like a beautiful planetary nebula that we can see here. And the last chapter was about galaxies through time, showing beautiful images of dancing galaxies and also group of galaxies that we could see through the eyes of JWST.
So, as I mentioned before, one of the things we utilized during this exhibition was huge light boxes that we used to create kind of a sense of a depth and immersion and a bit of a wonder, hopefully. But we also used the same technique on the totems you can see here on the picture to kind of draw attention to the highlighted area and introduce the chapters, the themes Milena just mentioned. And it was important for us to draw attention to them because guests could really get an in-depth knowledge on them. They could, in their own pace, get to know about the stories of the JWST telescope, about the specific pictures that were showcased. But what they could also do is listen to interviews with experts and scientists, some of whom even took part in the JWST telescope works. And that create kind of a way for the visitors to be able to explore the exhibition and its content, both visual and scientific, at their own pace within their own way of understanding things. The JWST universe, and especially the exhibition part, gave us a really amazing opportunity to create a space or a platform where arts can meet science or science can meet art. What you can see here is the reconstruction of a mystery and artwork where the inspiration is drawn from the telescope, but it doesn't treat it purely as a scientific tool, as a machinery, but rather recognizes its impact and significance within the kind of broader spectrum of today's culture. So this artwork is kind of one of the examples how our ecosystem of formats can create a space for those art meets science moments, which for us kind of illustrates the necessity to blend those fields and to create and foster a bit more engaging and a bit more accessible way of talking about science and finding different, more interdisciplinary ways of sharing knowledge. But we also ask ourselves how to invite people to the gorgeousness of space. We created an immersive experience, namely, we combine a very cutting-edge technology with the stunning visuals that the JWST telescope or imagery offers. And we mix them a little bit with some interactive elements and created an immersive experience from that. And it was a way to invite the viewers, in this case specifically every scientific community during a NOVA forum, to this captivating journey. And it's a way of connecting different means like beautiful imagery, new technologies, music, sounds, to create and offer kind of a blend of science and art, hopefully leaving people a bit more inspired and a bit more in awe.
So then we ask ourselves a question that is not a standard one. It's how to explore the cosmos with Lego. And that's how we come into educational program, the third pillar of the exhibition, of the experience of JWST experience. The educational program that offers a variety of hands-on activities and interactive workshops. We started those activities with the information package, preparation on the information package in various languages about what's the JWST telescope is and what are the different parts of it, and just showing the importance of the primary mirror and secondary mirror, also all the scientific instruments that were developed by several parties, and also this very amazing sun shield that was opening, and that was one of the most crucial moments to check if JWST actually gonna work. So this information sheet has also some additional highlights from giving the information why this given parts are at the telescope and what are they for. And with this information, we get into the second part of fun that was actually much more fun. And that was designing Lego models of JWST itself. So here you can see boxes with Lego bricks. These Lego bricks were not specially designed, but they were chosen from known Lego bricks, but they were designed in a way to create this little model. So there was a full instruction of telling us how to deal with building this part of the JW telescope, and you can play with it a bit. Part of JWST. We could also build from Lego some parts of the exhibition. So some nebulas that we could see on the photos. You can see on the left-hand side here, like the guide, how to build this nebula, and actually how to show to the audience, to the public, that these nebulas are in 3 dimensions. because all the photographs that we have are in 2 dimensions, and with all the experience that we designed, we wanted to show that these are the 3-dimensional experiences, at least 3-dimensional. And with that Lego bricks, we could actually work on this particular nebula to be more real. So we could also name some part of this nebula and so on. So we know that it's composed from a lot of gas and a lot of dust. So there was some scientific information also behind of that. So we could have here like 2 various activities related to either building the telescope or building the results that it was actually showing. So in this case, scientific phenomena. And these activities were intentionally designed this way that they could be either offered as with someone who knew exactly what this activity is for. So they could be animated. So the group of school kids could come and could be animated by the educator that was telling and introducing all these activities. But it was thanks to this informational sheets that were given to the kids and to the public. It was also self-guided. So you can see the photograph, the boy here who is actually playing with this on its own. So you could come on your own or as a family and without any additional animator or educator, you could actually build your own JWST or nebula. So it shows that this part of educational program offers a variety of opportunities. So you can do something for single people, for groups of people, for kids, for adults, because we know that, and we could also see that Lego was pretty fun also for elderly people. It's we know how great it can be, and then if we can put some information about the science and technology into that, that all created a great outcome of this part of JWST Universe experience, so of this educational program that has many ways to engage people.
And with that, we wanted to thank you for giving us a platform to talk a little bit about our way of creating science engagement opportunities for different audiences. If you're interested in staying in touch or you have any questions or possible opportunities, please don't hesitate to contact us. There are our contact info, emails from the people engaged in the project. Otherwise, visit us on the website. Yes. Thank you.
Thank you very much.
Hello everyone, I'm Dr. Priya Hassan and I teach at the University of here in India in the Maulana Azad University at undergraduate, postgraduate as well as PhD level. But I'll be talking to you about how we've been actually working on James Webb in schools, and this is just part of my interest of actually talking to school students. So let's see about how we can actually do such things. So we often visit various schools to talk about James Webb, and depending upon the school, if the school has the time, then we actually have a hands-on activity teaching them on how to actually make telescopes. But if the school does not have enough of time, then you could just have a talk in which we actually explain to students what exactly is the James Webb and why are we all so excited about it. Now, this can be done at various levels. That can be done at primary as well as secondary and higher secondary levels. And obviously, you have to adjust the pitch depending upon the kind of material that students have done in school at different levels, because certain things are known and unknown at different levels, and we accordingly pitch it. So first of all, we start off with the basic definition of what is the James Webb Space Telescope. It's an infrared space telescope. So what I actually like to do is to explain each of these terms in detail, in reverse. That is, what is a telescope, why go to space, and why do we need to study the infrared. So the first thing is, if you've had a hands-on session, then the students have actually looked through a telescope. Otherwise, you would explain to them a telescope essentially being a light gathering instrument. It basically gathers light from instruments, from sources, and the larger the mirror, the larger is the light gathering power. And then the telescopes also do give you the very important property of resolution and magnification, and that's how that helps us to actually look at faraway objects. And I would definitely talk to them about Galileo being the first one to actually look at celestial objects with the telescope. And even if you actually look at the size of the telescope which Galileo used, which was not very large, but the results that Galileo got with that telescope were revolutionary. For example, looking at the satellites of Jupiter, which was a contradiction to the geocentric model, as well as then, for example, the phases of Venus, which is again, it was almost observational proof that the geocentric model does not apply, because otherwise you would not get phases on Venus. And then, for example, the craters on the moon or resolving Milky Way stars. So that could actually give them the importance of why do we actually need to look at telescopes. And then the simplest telescopes, talk to them a little bit about reflecting telescopes and how one has to remember that even in reflecting telescopes, a lot of effort goes into the kind of design that you actually give the telescope. Because yes, you do have a mirror which will collect the light, you focus it, but if you put it at the prime focus, then you'd have problems like you have in the Palomar telescope, where the observer is literally on all kinds of positions doing circle skills, while you could also have additions like a secondary mirror giving you a Newtonian focus. You could have a hole in the mirror where you actually put a convex mirror, get a Cassegrain focus, or you add another mirror, a Coude mirror, to give you the Coude focus. And how this is also very important depending upon the kind of back-end instruments you have for your telescope. You may accordingly want to change this. And I love to tell students about how designing or innovation in telescope making is a very important art. And it is very important in the design of the telescope and how we actually put back-end instruments and use the telescope. So you could also see to it that you could put multiple instruments, back-end instruments at the same time, accordingly by using tertiary mirrors, secondary mirrors, and redirecting your light accordingly for observations. The next important aspect is to talk about the space aspect. And we talk about the atmosphere and how the atmosphere actually protects us from harmful rays, for example, X-ray rays, ultraviolet rays. But therefore, if we want to actually observe in the X-ray, it becomes essential to go out in space. And therefore, though the atmosphere actually protects us in that way, but if we want to look in different wavelength bands, we actually need to go out in space for X-ray, ultraviolet, parts of the infrared, and microwave, etc. So here we actually talk about space. For certain wavelengths, you have to go out. And then the other important thing, which is diffraction limited seeing. The high school students do know a little bit about diffraction, but the younger ones can be explained basically about how images go blurry because of the atmosphere. And if you go out in space, you won't have this thing. Then the other important thing which they easily understand is the observing time. Ground-based telescopes have limited observing time, but if you're out in space, you do not have to worry about the day-night cycle. And for example, that these telescopes can be a survey mission and an observatory mission, and how even they or anybody in principle can actually observe with the James Webb by actually putting in proposals. Basically trying to show them how there's a certain level of democracy and freedom in science where anyone in principle can use the best of telescopes depending upon his or her science case and justification. The next thing I talk to them about is infrared. Why do we need infrared? It's essentially 700 to nanometers to 1 millimeter. Herschel discovered it. What is actually infrared, and where is it actually used? What is the importance of infrared? Maybe a little bit about black body radiation and who emits in the infrared as being good infrared emitters. And basically, why does James Webb need to do infrared? Because James Webb is essentially a telescope to look at origins. And if you want to look at origins, you are, for example, looking at young stars. They are going to emit in the infrared. You're looking at high redshift objects. Their optical emission will be now in the infrared, and various reasons why we need to do that. And then I talk a little bit about the first light images of James Webb, so showing them the Eta Carina, as well as Stephen's Quintet, S-Max, as well as this thing. So it covers most of that. And then we talk about a little bit about the future, that then you have the Raman Space Telescope, which would be the successor to James Webb, and how a little bit about Hubble, because many of them have heard about Hubble, comparing James Webb with Hubble, and how development in science, another very important essential thing, is about the engineering or the instrumentation of these instruments, that this is really cutting edge instrumentation and engineering, and the kind of things that have been used for James Webb. So I think I try to make them convinced that astronomy not just includes looking at stars, it also includes a lot of stuff about innovation in telescope building, as well as high-end engineering. So thank you.